So let's begin. So, hello everybody. Thank you for joining us and welcome to the ASTRO 3D Easier Astronomers in Australia seminar series. My name is Inferring. I'm a PhD student at the Australian National University. My co-chair is Anisha Hassan from the University of New South Wales. Before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and the Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I am speaking with you today from the land of Ngunnawal and Ngambri country. My co-chair, Anisha, is joining us from the land of Badigo people. Our first speaker, Alec Thompson, is speaking to you from the Wajak people of Ngunnawal land. And the second speaker, Dag Evensberget, is speaking from the land of Jabal and Jarawa people of the Tumba area. We pay our respects to the elders past and present and extend the respect to all First people joining us here today. So why are we here? This series is facilitated by ASTRO 3D, the ARC Center of Excellence for All Sky Astrophysics in 3 dimensions. COVID-19 has affected our ability to travel and present at international seminars this year, especially for us in Australia. The time zones mean that often meetings take place at 2 or 3 in the morning. This lack of opportunity to network could disadvantage junior astronomers when entering the job market. This series aims to combat these issues by providing a platform for junior Australian astronomers to present their work to the world. There will be 2 talks over this hour. Each will be 20 minutes in length, with 5 minutes for questions at the end of each talk. Please save your questions until the end of each talk. Feel free to use the chat function to ask your question if you prefer. And Anisha can read it out for our presenter. These talks are being recorded and will be placed afterwards on the ASTRO 3D YouTube channel for educational and scientific purpose. By being here today, you are agreeing to abide by ASTRO 3D's meeting code of conduct. I have already warned the speakers of this, but because of the limitation of Zoom, I will need to interrupt with 5 minutes to go in each talk. So we will have our next speaker. Our next speaker is Dag Evensberget. He is a PhD student at the University of Southern Queensland. And Dag, you can share your screen now.
All right. So thanks a lot to ASTRO 3D for organizing these talks. And my name is Dag Evensberget. I am a PhD student at the University of Southern Queensland. I'm originally from Norway, in case anyone is wondering about that. My talk is called Winds of Young Suns, Inferring the History of the Solar Wind from Stellar Magnetic Field Observations. So at USQ, I am part of something called the Star Winds project, where we aim to produce the largest set of 3-dimensional wind maps for young sun-like stars. I think we can say that we've done this now, at least the largest set that is produced using exactly the same methodology. And we'll be looking at some of these results today. Currently, I am the only PhD student in this project, but I have a lot of people helping me, postdocs, my supervisors, and we have associate faculty and other collaborators. So, the strength of the solar wind in the deep past. What I mean by the deep past is sort of from the formation of the sun. Is poorly characterized, but it can be constrained by studying other young sun-like stars. And this is what we are doing using the star winds data, or that's what I'm going to talk about today. The procedure is that we map the stellar surface magnetic field using the technique of Zeeman Doppler imaging with polarized light. Back to the previous talk. Then that is used to drive three-dimensional numerical simulations where we use an alpha wave heated corona. So the corona in these models is heated by magnetic alpha waves emanating from deeper layers of the star. From these three-dimensional numerical simulations, we can produce stellar wind maps that cover the stellar corona and the inner astrosphere out to the orbits of or the inner planets of Venus and the Earth and Mars. The integral characteristics of the wind determines the rate of stellar spin down, or at least the angular momentum that's lost by the star. And indirectly, this largely determines the history of the solar wind, but with some caveats that you shall see. Also, magnetic variation and magnetic cycles is a bit of a joker in this relationship because they modulate the rate of stellar spin down. So this is a diagram from Gallet and Bouvier that shows the stellar rotation rate for sun-like stars as a function of their age. So we see here that there's a phase of contraction before the star goes onto the main sequence. Then once we're on the main sequence, the main effect that changes the rate of rotation is wind breaking. So angular momentum lost with the stellar winds. And at about 1 billion years of age, the sort of state of the star when it formed, whether it formed as a rapid rotator, the blue curve here, or sort of regular rotator, the green curve, or a slow rotator, this information can no longer be really seen once the star reaches this part past 1 billion year, because no matter, we see here that the angular velocity is proportional or inversely proportional to the square root of the age of the star. And how fast did the young sun spin? Well, like I said, as a consequence of what I said, we don't really know. We don't know if the sun formed as a rapid rotator, having a blue curve, or if it formed as a slow rotator, following the red curve here. A feedback mechanism is responsible for this convergence. So the stellar rotation rate through dynamo effects determines or it has a large influence on the magnetic field strength, which together with the rotation rate itself determines the wind mass loss from the star. Then again, the wind mass loss and the magnetic field determines the stellar angular momentum loss, which of course then slows the star down. So we get this, essentially this feedback here, leading to the convergence of the fast and slow rotators at about 1 billion years. There is also a relation between rotation or period of rotation here on the x-axis and the Zeeman Doppler imaging. So the magnetic field strength observed with Zeeman Doppler imaging, which is the technique that we have used to see the magnetic field maps that I'll show you in a moment. Just take note here that at the given period of rotation, there is a spread of about an order of magnitude in this magnetic field strength. So this magnetic variation also affects, obviously, the magnetic field. And in that sense, it also plays into this feedback mechanism. In this, I talked about the Star Winds project and the biggest set of magnetic maps. So here are the 30 stars that we have been modeling So for these 30 stars, we have the surface magnetic maps. What characterizes these stars as well is that they are cluster stars, so the ages are pretty well known. We have here the Hyades, the oldest stars at 650 million years, down to Beta Pic at just 24 million years of age. And you can see from the rotation and from the radius and the mass and so on that these are young sun-like stars. They're not solar twins, but they are quite a lot like the sun. If I plot the evolution of the rotation as a function of age here now in gray, you can see that my stellar sample sort of matches up relatively well to the spread that we saw before. There's a large spread that for the AB Dor and Pleiades clusters, about 120 million years old. And then there is a much smaller spread for the older clusters. Here is essentially what I'm using to drive my MHD models, my numerical models. And the surface radial magnetic fields. So here from the left towards the right, each column is a younger group of stars than the column before. If you look from the left to the right, and you'll see that there is it looks a bit darker over here, which essentially means that there's the magnetic fields are stronger for the youngest stars. We also have these two particularly rapidly rotating stars, BD07 and LOPEG, where you see a lot of detail in the magnetogram. This is a feature of the Zeeman Doppler imaging methodology, that the more rapidly the star rotates, the more detail of its magnetic field can be observed. So there might be more detail for the older stars here as well, but we wouldn't be able to see it. And of course, this is something that we have to account for when we create the wind models. What you do see with the strengthening in the magnetic average field from left to right, that's however, that's not an artifact of that's a robust result that does not just happen in ZDI, but in other ways of measuring the magnetic field as well. So from these surface maps, we can extrapolate. After we've run our models, we can essentially plot the magnetic field lines in 3 dimensions. Typically, you get a structure, a sort of dipolar structure like here, but where you have what's called helmet streamers, these elongated magnetic field lines around the equator, which is also shown here in the theoretical image on the left. The line here where the magnetic field is 0 is not a straight line. It's not perfectly across, right? As we saw, these can vary quite a bit, and we can sort of recognize that when plotting it in this way. Now, looking at all the 30 models, we see that most of them have this sort of dipolar shape, but there's large excursions from sort of between the north and the south region of the magnetic field. So they're not all just like this one. Some of them have more complicated shapes, and some of them don't really even have a dipolar shape, but a more complicated shape that is more reminiscent of the sun at solar maximum. Furthermore, with the same wind models, we can plot and show that this Alphen surface. The Alphen surface functions as the torque arm when the stars are losing mass. This distance from the star to the Alphen surface functions as a lever arm that amplifies the loss of angular momentum. So the larger the Alphen surface, the larger the angular momentum loss. This gray translucent sheet is the current sheet shown here in a sort of slice, and this is the region, or in my models, this is the region where the radial magnetic field strength is 0. Once again, Looking at all the 30 models, we see that in general, we have this dipolar shape for the Alphen surface. The orientations vary, same as we saw for the magnetic field itself, from essentially 90 degrees of inclination to the axis of rotation, which is just up and down here, to 0 degrees of inclination. If you have rapid rotation and an inclined dipole axis, such as here, then you can get this wrapping of the current sheet around the star. And this star also has a very large angular momentum loss, as we shall see later. The two oddballs, BDO7 and LOPEG, the very rapid rotators, have also their Alphen surface affected by the rapid rotation. So that's why they are looking a bit funny. You can see a little bit of that in some of the other stars as well, but especially this one is quite interesting looking. We can also calculate, as I said, the wind pressure past the orbit, or the would-be orbit of Venus, the inner one, the Earth, and Mars. We get these spiral shapes. So the solar wind sort of streams more or less directly out, but we have regions of denser and less dense wind coming from the regions of open and closed magnetic field lines. Let's go back. So when the magnetic field lines are closed, then you have the slower wind coming from those regions. And this gives rise to these spiral structures, which is also matching well to theory. And this is a bit preliminary, but here's the wind pressure for all the stars that I have finished so far. So we're pretty much done here. And you see in general, you see either like a two-armed spiral, or sometimes there's more than 2 arms, such as the one I showed initially here. There's 3 really. And the amount of wind up is dependent on the rotation rate of the star. So the 2 rapidly rotating ones, they have much more wind up than this one, for example. By integrating the mass flux, we can calculate the total mass loss, the wind mass loss. My models here are shown in blue. These two, this is the sun in solar minimum, solar maximum is these 2 values here. The sort of tan color represents other people using similar methodology as me. So you can see that, well, first of all, you can see that StarWinds has a lot of models. But secondly, you can see that this actually matches really well. The green region up here, these are ideal MHD models where the temperature of the corona is set as an initial condition, while in my models, the temperature of the corona is arising from the heating from Alphen waves. So in some sense, this is more physical, but you might also argue that you're just pushing your uncertainty into different physical parameters. So anyway, you can argue both ways. And the background here is some population studies by Victor C. So you can see that the mass loss values that we get with our methodology is on the lower end, but inside the spread of the observed values that are inferred from population studies.
Dag, you have 5 minutes.
Thank you. That should be good. To know the effect of this stronger wind on an Earth-like planet, a key parameter is the magnetospheric standoff distance, which is the distance at which the Earth magnetic field sort of dominates over the solar magnetic field. So this is, you see here, this value for all the different stars in the study, and even for the ones that are the strongest, we don't really see this value dropping below 5 or 4, which means that the steady wind shouldn't have posed too much of a threat to the atmosphere of the young Earth. So that's interesting. That's a bit different from M dwarfs, where this is always seen as a problem. We can compare we can calculate the torque, which again is the angular momentum loss or the spin down essentially. here I show it as plotted against the average magnetic field strength, and you see there's a large amount of residual here, a factor of 64, that essentially is unexplained by this parameter alone, by the field strength. If instead I use the total surface flux of the star, we get a much better residual here of a factor of about 8. And finally, if I also scale the torque by the rotation rate, so essentially dividing through here by the stellar rotation rate, we get quite a small residual here, only a factor of 4. However, this residual that we are left with now, I attribute mainly to magnetic geometry variations. So not like strength variations, but variations in the shape of the magnetic field. So now with those results, we can revisit the torque-age relation and sort of superimpose it onto the rotation curves that we saw initially. So this is again the Gallet and Bouvier curves here. I've added a few just to show sort of like how these stars would be expected to move as they age. And the little line segments that I have added to each star represents the angular momentum loss of that particular star. So they're not too bad, but you see here that they don't always fall exactly on the line. So the numerical models suggest that there is actually variation here that is not just explained by the stars following on these curves, but by something else, and that something else is essentially variations in the magnetic geometry. We also see, or we can infer, that these variations have to be transient. So, for example, this star N here that sort of is headed down here seemingly in the graph. If you compare it to L, which is pretty much following the curve, this difference in where they are moving cannot persist for long times, right? Because that would mean that we wouldn't see this convergence at 1 billion years of age. So essentially, these magnetic variations that we were talking about initially, they cannot persist for very long time scales. Otherwise, it would jeopardize the shape of this plot in general, the mean here and the spread. Just note as well that there is the solar variation here. So the sun has 2 line segments going out of it, one representing solar minimum conditions and one representing solar maximum conditions. And this is the solar cycle, right? So over like a time scale of some tens of years, the sun varies between these high and low torque states. Most likely, some of these other stars also would have a similar variation, but to know more about that, we would have to observe the star many times over like many years, and I don't have access to that kind of data, but as we keep following up these stars, that will be interesting to do in the future. And finally, we just see here that stellar observations may underestimate the field strength for some of the slower rotators. I mentioned it a bit before that when you have faster rotation, then ZEI sort of recovers more of the magnetic field. There is some indication of that here as well. And that's also something that we should look more at with our models in the future. And that's the end of my presentation. So thanks for listening to me. If you're interested in this kind of stuff, then have a look at our paper, which is out now. It's accepted anyway, so it's the PDF is available, and soon it'll be like published and everything.
Cool. Thank you, Dag.
Thank you.
Any question from audience?
We do have one question in the chat. I can read it out. It's from Darren McQueen. They are asking if so the rotation rate is constant for at a given time when, for example, when it is more than 1 gigayear for sun-like stars. Do we know if this relationship changes with mass or significantly larger or smaller main sequence stars? would it be possible to infer mass using rotation rates at times that are greater than 1 gigayear?
Right. Yeah, I'm looking at the question here as well. So the rotation rate is it is dropping. It's never constant, but the change in the rotation rate is constant past this 1 gigayear. And this does also apply for quite large. It's not just young sun-like stars. I'm not sure about stars that are totally different, like A-type stars and so on. That's a bit past what I have looked at. But if you take stars with mass that's about half the solar mass or 1.5 times the solar mass, you'd essentially see a similar shape, but some of these features move around a little bit. So yeah, the relationship changes, but so the nature of it isn't totally changed. It's similar. So then, would it be possible to infer mass? So the mass loss, or using rotation rates? Yeah. So that's what. Yeah. Okay. So I think you're asking because I don't have any sort of stars in this region. But there's no real reason why we can't also model stars in the region between the age of the Hyades here at 650 million years and the sun. In a sense, this is because the stellar magnetograms that I have access to just happen to lie in this region. And it's not so easy to go further into the past because it's occluded by accretion disks and so on, but going towards older stars should be possible.
Cool. Thanks, Dag. Very clear and great talk. Thank you.